I will explain problem E from division 2, travel plan. So we have a graph, which is like standard binary tree. First of all, we have the zero level, which consists of vertex number 1. Then we have the first level, which consists of two vertices, number 2 and number 3. Then we have the second layer, which consists of 4 vertices. In general, ith level consists of vertices from 2 to the power of I to 2 to the power of I plus 1 minus 1. And parent of vertex number I is I half. The question is also the last layer, which is something like around logarithm of n. It is not full, maybe. Yeah, because it ends not at such number, but it just ends at the number n. The question is, so we have a travel plan, which is just an array. Let me write. Travel plan equals an array of length n of integers from this set. And we need to find the following sum. Sum for all travel plans, then sum from all I from 1 to n, then sum for all j from I to n, and we consider the maximum of ak, where k is on the path between I and j. So this is the thing that we need to calculate. So as I said during the screencast, again, I will not implement this problem right now because it is in the screencast. You can rearrange it as sum from I equals 1 to n, and sum from j equals I to n, and then sum for all a which are travel plan and this maximum. The interesting part is that this only depends on the length of this of the path. So let's rewrite it as follows. Sum of L equals like from 1 to infinity, I don't know, to n, for example. And we calculate the number of paths with L vertices times the sum for all A travel plans maximum of just like L numbers in A. So after that, the problem is kind of two separate things. You need to, for each L, find this thing and find this thing. Yeah, so actually there is some sort of associativity in such sums. So you can put brackets like this. Or you can put brackets like this. And this will be the same thing. I mean, okay, like this, but also there is some from L equals 1 to N. No, 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 no. I messed up. I messed up. I mean, okay, what I mean is just the problem is now two different parts. So you can just multiply AL times BL. AL is the number of paths with L vertices, and BL is this maximum. So let's solve these two problems independently. First of all, BL. So we have some fixed L. We need to find this sum. Yeah, so we have some L numbers in array A, and we take maximum of them. And we find the sum of such numbers among all possible arrays. First of all, let's just only look at important numbers. So let B in A are important numbers, which are used in this maximum. In this case, we just consider sum of all, first of all numbers A without B, then sum for all B's, and then maximum of B. Let's continue. This actually does not affect the answer. The only thing it does is it multiplies the answer by the number of ways of choosing these numbers. And this is just m to the power of a minus b, which is m to the power of n minus l. Now we need to find this thing. We can rewrite it as sum from x equals 1 to m x times number of ways to get maximum x. And this is some sort of exclusion inclusion. What do I mean? So assume that you need to calculate the number of ways, calculate the number of arrays of length L in which the maximum is x, exactly x. This is kind of hard problem. Let's simplify it. Let's find so number of ways, maximum is x, exactly. Let's instead calculate the number of ways in which maximum is at most x. And this is easy because you just need each number to be between 1 and x. And in this case, it's just x to the power of L. But you have some maxima which are less than x. So let's subtract the number of ways in which maximum is at most x minus 1. As we already know, the answer is x minus 1 to the power of L. But now if we subtract these two numbers, we just get the number of ways in which maximum is exactly x. So this is the answer. Okay? So what do you do? What you need to do here is just to sum all such numbers for all x from like 1 to n, 1 to m. And in each case, you multiply x by x to the L minus x minus 1 to the L. Okay? I actually a bit simplified it during the contest, but I think there is no need. This is also quite simple. So now you can calculate BL. for all L that you need. Now we need to calculate AL. So number of paths with exactly L vertices. I think there might be several possible ways to do it. I did it in like logarithm of n cubed. What I did is just look at all possible paths in a tree. Any path looks like this. There is some starting point, then there is some LCA point, and there is some finishing point. And the path looks like this. So there is also always some LCA point, and one of the ends is in the left subtree or equal to the root, or in the right subtree or equal to the root. So what I did is I iterated over all possible heights of this vertex, all possible heights of this possible vertex, and this vertex. So assume that I, j, and k are fixed. What do we do then? So if they are not D, where D is the lowest layer, where there are some vertices present and some are not present. So if all these numbers are less than D, then this is easy, because you just need to choose I, vertex in the ith layer, and there are like 2 to the I ways to choose it. After that, you need to choose a vertex in the jth layer, and there are 2 to the power of j minus 1, j minus I ways to choose it in this subtree, but minus 1 because you need j in the left subtree and not in the whole subtree. But maybe sometimes plus 1 if j equals I. So you need here to actually write maximum of 0 and j minus I plus minus 1. And the same goes for 2 to the maximum of 0 and k minus I minus 1. So if all three numbers are less than d, then this is easy. Also, if I equals d, then you just need the number of vertices in the lowest layer. And all these technical details are in the screencast. You can find them there. So finally, there is a case when I is less than d, but maximum of j and k equals d. In this case, there are still, it's still not that bad, I mean. But what I want to say is that there is a certain moment in which the layer d ends, and after that you have only layer d minus 1. And this moment, it is exactly in one vertex I. So there is some certain vertex in ith layer, such that there is this phase shift from having d layers to having d minus 1 layers. Okay. Then let's consider three cases. Either I is here, or I is this vertex, or I is here. The three cases. First case, I is in the left part. If I is in the left part, then actually the answer is totally the same as here, because here you do not have any irregularities. Just instead of, let it be rth vertex here. So there are r vertices here. In this case, instead of 2 to the power of I, you replace it with r. And these two are the same because you just choose some ancestor of depth j and some ancestor of depth k. And there are, this is full binary g in this part. So the second case is also straightforward because you just know how many So since I is just fixed, you know exactly how many numbers D here and how many vertices of layer D here. It is possible to calculate. First of all, you have like the total number of bottom vertices. It is like n minus 2 to the power of D, but plus 1, I guess. This is the total number here. After that, you need to subtract r to the power of 2 to d minus I. This is number of vertices here, which correspond to vertices here. So this is number of vertices in this place. And now you can just divide it into two parts. So like in the left part, there are minimum of this number and 2 to the d minus 1 minus r. And in the right part, there are this number minus this minimum. So you know how many d vertices in the left part and in the right part. And you can, if needed, replace these powers of 2 with these pre-computed numbers. And in the third case, then see 0. Yeah, because j or k is equal to d, but there are just no d's either in the left tree or in the right tree. So that's it. There is a certain formula to find r, but it is also found during the screencast, so you can look there if you are interested. I think I will just finish with this problem. I think I explained it well. The important thing is here I iterate from 1 to n, but it is quite big. The important observation is that actually L cannot be quite big. Yeah. So any path should go from some layer to some upper layer, and then from some upper layer to some lower layer. The number of layers is at most logarithm of n, which is like 60. So any path is at most 121 vertices long. So you definitely do not need any more than 121. So we can put here like minimum of n and 121. I think that's it. So let me write the total asymptotics. So first of all, you need to find these numbers. I found them like in log n times m time. So the right numbers have these asymptotics. What about the left numbers? I spent kinda log n cubed, I think. And maybe all this is multiplied by log m. I don't know, because I also made some modular operations modular m. Actually, it is not needed, but just in case. Maybe we need some inverses, although we didn't need to do some inverses. So just this. Again, if you need the implementation, look into the screencast. Bye.